G'day chemistry students, in this video we're looking at dot points 5.1, 3 and 4, and in particular our focus will be on equilibrium systems. Let's get into it. Now before I get into chemical equilibrium, I wanted to look very briefly at what equilibrium looks like in physics. I think that it gives a little bit more of a better visual and I guess generally from a scientific perspective helps to explain what equilibrium means generally. So in physics, when we're looking at equilibrium, we're mostly looking at the balance of opposing forces. So for example, in this aeroplane that's flying, there is going to be a balance between the lift and the weight, pushing the plane up and pulling the plane down, as well as a balance between thrust and drag. And so if the plane is not accelerating, it's not lifting, it's not dropping, it's not speeding up, it's not slowing down, it's not changing directions, what you're going to find is that forces in the up, down, forward, back, side to side directions are all going to be balanced. If you change one of these forces, maybe you increase the lift or increase or decrease the thrust, what's going to end up happening is that there's going to be a shift away from equilibrium. There's no longer going to be balanced and the plane is going to move in a different direction. Broadly, what we're looking at with equilibrium is a balance of some sort between two or more things. So from a chemical perspective, what we're looking at is a balance between two reactions, a forward and reverse process. So what I have here is a simple reaction, A plus B forming AB. Its reverse, AB turning into A plus B. So very similar to some of the reversibility stuff that we were just looking at in the previous lesson. But if something is in equilibrium, what that means is A and B can turn into AB, and AB can turn back into A and B as well. Generally, when we're looking at equilibrium, this is happening at the same time. And when we have this forward and reverse process happening at the same time, we specifically call it dynamic equilibrium. In this sense, we have reactants turning into products and products turning back into reactants, and that's happening at exactly the same time, at exactly the same rate. So what you'll see with these ants in this GIF is that one ant is taking from the reactant pile to produce products, and the other ant is taking a product and turning it back into a reactant. And the rate at which that change of reactant to product and product to reactant is exactly the same. Now, this isn't showing a chemical reaction physically, but I think is a really effective analogy to show that the rate of reaction is the same. That we don't have lots of reactants turning into lots of products, but not many products turning back into reactants. That it's showing the rates are exactly the same. And that's the really important part to focus on with equilibrium. There's a pretty common misconception that at equilibrium, there's an equal amount of reactants and products. But as we can see here in this diagram, there are actually more reactants and there are less products, but the number of reactants and the number of products doesn't change at any one time. The number of reactants stay the same, the number of products stay the same, but the number of reactants and products are not equal. And further to that, and this is the important part, the definition of equilibrium, the rate of the forward and the reverse reaction are the things that are the same. So when we have a reaction that is actually in equilibrium, there are a few set of conditions that need to be met. In particular, one of them is that the system must be closed. Now, what that means is that all of the matter that is a part of both the forward and the reverse reaction are unable to escape, that all particles at all times, all mass is able to be in contact with each other so that they are capable to react in both directions. If you have mass loss, then you're not going to be able to enable both a forward and reverse process to be occurring at the same time. So in an open system, there can be a transfer of energy, but also because, like in here, there's a cap that's being taken off, you also have a transfer of mass. In particular, in this case, what we'd be looking at is a potential transfer of gas. So if there were gaseous reactants or products in an equilibrium in an open system, those gases would be able to escape and you wouldn't enable equilibrium to occur. Compare that to our closed system over here where those gaseous particles or any mass wouldn't be able to escape, but there can be a transfer of heat to enable energy changes if they were needed. You can also have isolated systems in which you stop heat transfer. We're not going to focus on these ones really that much at all in the scope of this course, but you can have systems that exist like that as well. There are a couple of other conditions as well. In particular, the forward and reverse processes need to be spontaneous, or I guess near spontaneous. So that means the delta G is about zero, thereabouts, or as close to zero as possible. And we can determine that using our delta G calculation that we learnt about from Module 4. What you'll also need is to ensure that both the forward and the reverse processes can actually happen, that they can actually proceed. And that means that the activation energy of both the reverse process and the forward process is being met. So to sort of summarize, as long as you're not losing mass, your system is closed. As long as both the forward and reverse reactions are spontaneous and there is enough energy within the system to ensure that all activation energy needs are met, you're probably going to find that your system is going to end up in some form of dynamic equilibrium once you put all of those reactants together. What can happen though is you may see some examples of either static equilibrium or non-equilibrium systems as well. So something that's in static equilibrium, it's a little bit of a weird topic to talk about, actually. It's not one that comes up in chemistry very often, but it is a part of your syllabus. So we're going to talk about it very briefly, but not spend too much time on it. The course mostly focuses on dynamic equilibrium. But I guess for static equilibrium, you can technically say that something is in equilibrium if the reaction rate of both the forward and the reverse process is zero. I will note as well that generally speaking, a lot of these reaction conditions that are highlighted up above still sort of need to be met. We're usually still working in a closed system. So the example that you might see thrown around is that carbon as graphite can turn into carbon as diamond and vice versa as well. And in this scenario, you have your two structures or two allotropes of carbon, but having either of those reactions actually occur with any large reaction rate is quite difficult and generally doesn't happen, certainly not at a fast reaction rate. So what we say is that we would observe this to be static, that if we had a piece of carbon as diamond, you wouldn't really see it turning into graphite, and vice versa, because the reaction rate of both of those things are just that slow. We also have non-equilibrium systems which don't meet a lot of the conditions that are above. In particular, in class, we'll spend some time looking at combustion and photosynthesis. I've also created a Venn diagram to sort of summarize some of the differences between static and non-equilibrium. They are quite similar in a lot of ways, but fundamentally are quite different. We'll break this down a little bit more in class. Thank you very much, everyone. In the next video, we're going to be spending some time looking at some of our more physical chemistry aspects around collision theory and thermodynamics and stuff to explain how and why equilibrium systems do what they do. But until then, have a good one.